Great. Well, thank you for having me. Thanks to Jeff for putting this together, and Matthias. It's great to be here. Let's just jump right in. So, tell you a little bit about myself. I'm currently co-founder and CTO of a company called Fritz. We will talk a little bit more about what Fritz does later on. But in terms of my background, I'm pretty much all about engineering. So, building engineering teams, building products, lots of different domains, consumer, enterprise, B2B, B2C, all that fun stuff. Some notable things. I was one of the early folks at HubSpot just across the street from here, and had a really fun ride there. Whoa. Spent some time at a company called Babaco running their engineering team. Also Jana Mobile, if you guys have heard about that. So I've done the rounds in Boston. Techstars here, I participate in the mentorship program there. So if anybody's ever been a Techstars company, you may have met me around there. So that's a little bit about who I am. I was wondering if we just do a quick thing with the audience of who you guys are. So hands up if you're on the engineering side. Okay, hands down. Hands up if you're on like product. Okay, and last group, anyone who's not in engineering or product. All right, so we've got a pretty good distribution of folks. Just gonna make that not as for me. So what we're gonna talk about today is artificial intelligence, machine learning, deep learning. I'm not going to get into all the semantics around why we call what we call, but I want to talk more about how people use it rather than how you do it. So this isn't a talk about training. This isn't a talk about modeling. This is a talk more about what are we able to do with AI today and how can we use that information to build applications, to actually do things that people can see that go beyond R&D, real applications. Cool? And I want to start with AI, just the general state of things. I don't know that this would come to a surprise to anybody in this room, but we have moved well beyond the stage of this being a moonshot. It wasn't that long ago that there was a time that everyone would have thought AI is this thing that people have been working on. You know, the first concepts were put together in the mid-40s, the 70s, or when we started working on deep neural networks, and we didn't have all the pieces put together until relatively recently. But now we've got the compute, we've got the architectures, we've got the data. We're actually able to teach computers things and let them think for themselves. There's limits to what it can do, obviously, but that's long gone behind us. We're long past the point of saying this is just research science. Nobody's ever been able to ship anything with it. There are a lot of things still catching up, though. So I look at data and I think, yes, we've got tons and tons of data, and we're more or less there in a place where we can start using that for artificial intelligence type purposes. However, there are still some problems around like feature engineering. How do you aggregate that data? How do you summarize that data? How do you make that data available at both training and inference? All of those sorts of things are still problems. So there's some catching up there, but we're probably more than halfway. Architecture. You look at the way that most models today are structured, and they're based on some sort of research that happened often at universities. But those labs have been working on this stuff for decades at this point, and there are fairly mature architectures that are good at all sorts of different computer vision problems. In fact, on some of the architecture, we're even looking at certain types of models that were never designed to do a computer vision problem, but when trained on computer vision type data, seem to work well. So there's something that we're getting close with these machines actually being able to think. On the training side, we've got really good tools available today, probably better than most technology products at this stage in this maturity. We've got things like, Keras, Caffe, TensorFlow, all sorts of stuff supported by Google and Facebook. Microsoft has some tools. They're not my favorite, but they have some. And then stuff that we're still probably farther down on the road, but we're catching up around deployment user experience. So how do we get the tools into people's hands so they can leverage artificial intelligence or deep learning in a normal application in a way that they would use a piece of software as opposed to the way that they would think about something in the lab? And then user experience. That one's probably the farthest behind, but we'll talk more about the actual application experience. The other thing I want to do up front is talk about edge intelligence. So Fritz, my business, we specialize in edge intelligence. So we're going to talk more about that, a lot about that. But I don't think it's right to talk about artificial intelligence if we're not talking about how things are getting small. If you think about traditional AI, it's this big sort of data center focused thing. People assume it's all about big data and having clusters of GPUs and you're running, billions and billions of operations. And that's true. We tend to do that for the training of models, but the actual place where models are getting run is getting smaller and smaller and smaller. That's a microcontroller on the right-hand side there. And those are capable of running neural networks. There are something like 40 billion microcontrollers sold this year. There are hundreds of billions already out there in the world. And the math that happens in a deep neural network is a fixed amount of math. We know exactly how many calculations and operations it's going to take. There's no variable there because when the model is trained, you've frozen that in time. And what happens is we are able to take those instructions and through a process of software and hardware optimization, run them anywhere. Now, I'm not saying you can take a super small microcontroller and run a really intelligent computer vision model at a full frame rate of 30 frames per second. But you can run lots of interesting things directly on a microcontroller. I don't have the video here, but if you guys are curious, there's a great one that Pete Warden was talking about recently, taking a Raspberry Pi or Raspberry Pi Zero and connecting it to a 4-cylinder engine. What they were having it do is use a deep neural network to optimize the combustion cycles of the engine. And so they went from an engine that kind of had these wildly inaccurate combustion cycles to one that was perfectly on. Every cycle was igniting at the exact point that it thought it would, which means the engine runs smoother, it uses less fuel, all that fun stuff. But that's running on a very, very inexpensive microcontroller, not a GPU, not a TPU or anything like that. It's running on tiny little objects that you can fit in small devices for a reasonable amount of money. The state of AI today for a lot of applications is like this. You've got a bunch of data that gets fed in from things like databases, wearables, you download a bunch of stuff from a car, whatever it happens to be. Then you kind of upload it to a cloud, and then once in the cloud, you do some processing. You process the input data, maybe you do some feature engineering, then maybe you actually do some inference, and you send you send a bit of information back down. That process is working fine, but it only enables certain types of scenarios. What we want to work toward is having everything all in the same place, all on one loop. That's how we unlock some of the most powerful applications for what AI can actually do. It's not turn-based of do a thing here, send it up to the cloud for computing, send it back down and tell the person what the output was. It's rather, let's put the sensors, the processors, the models all in the same place, and let's make sure that loop can run really, really quickly. And that is what edge intelligence is all about. It's taking the model and moving it to the sensors and the data, rather than taking the sensor data and moving it up to the cloud where the model is. That's the world that we're transitioning out of today. The majority of things that we're working on are probably being inferred by cloud-based services, and we're moving away from that to places where microcontrollers and other types of chips are running it. This unlocks a whole bunch of new, very, very interesting applications. We'll talk about some of them in a minute. But the really big ones are things where you just can't do it unless you move the processing to where the data is. So things that use live video, things that use a lot of audio, self-driving cars, things where privacy is a concern, things where you would want to train the information on a source only available, like Face ID for those of you with like iPhone 10 pluses. Those types of things only happen when you put the sensor and the processor and the model together. And therefore, my prediction is that edge intelligence is going to be greater than anything else in the AI space. If we look at the amount of things that can run machine learning models, the number of devices they will be in, the cost structure of what's happening to those over time, the number of applications that are powered by it, it's way, way bigger in the eventuality of this market than anything that's running cloud side. Right now, the cloud side stuff looks a lot like, let's take a look at a map tile and determine where that might be. Let's do some sales predictions. Let's figure out if this lead is likely to close. Those types of transactions, they're probably happening at hundreds of thousands a second. But we're going to be moving to a world where hundreds of billions of these things are happening on devices that are all over our bodies, all over our homes, all over the world. So that being said, let's jump into some of the application side of things. This is my formula for practical AI applications. How confusing. I don't know if anybody would jump to conclusions. But on the left side, those are sensors. So take a sensor, take an expert times 1 minute of their time, and that is an AI application. So think about combining a sound with a person who knows lots about recorded music, and you get Shazam. It's like a machine learning type of problem. And we'll go through a bunch of these. But let's just take here, because this filter is going to come in handy over the next bunch of slides. Taking sensors, plus 1 minute of an expert's time. Another way you can think about this is if you've got a trainable dog. I know there are lots of dogs that are not very trainable, but if you could take a dog and teach it to do one thing and teach it with reinforcement techniques, that is a good formula for filtering out whether something would make a decent AI application at this point with the current technology we have available. So we're starting with vision. This is a camera sensor. One of those. And there's a lot of applications probably on people's phones in this room right now that are powered by deep neural networks, and you might not even realize that. So Snapchat is one of the oldest in this regard. They had acquired a company for $150 million to buy a team of people who were specializing in running deep neural networks on device. And that is what powers so many of the interesting things behind the creativity tools of Snapchat. It powers face detection. It powers finding the different points on the faces, doing depth mapping. It powers, they have filters where you can speak to them, and using a trigger word, it will do something in the filter. They don't talk about machine learning. It's not a machine learning company, just an application that happens to be unlocked by having machine learning on the device. Again, this wouldn't work if we had to go with the cloud round trip. We're not going to take every frame of video, push it up to the cloud, put a filter on it, send it back down, and expect people to create a lot of media that way. It's a slow process. So these types of things are really only possible when we move it. The Instagram example is a thing called style transfer. So it's a way of taking a deep neural network and training it instead of on some logical thing, and training it on what an artist would do. So you can take a color palette that a certain type of artist would use, or the lines that someone would use, or the unusual structures of a picture that someone like a Picasso would use. And you can teach a little neural network to figure out how to take any photograph you've taken and re-envision it through that artist. And then finally, there's a bunch of stuff happening in the AR and mixed reality space. Wayfair here, they've done extensive work to get 3D models of all the pieces of furniture they sell on the site. And then they deploy them through the mobile app so you can actually place them in the room. And that's using, again, machine learning to figure out what are the surfaces that are around here? Where are they? What are the parameters that my phone is getting in terms of pitch and yaw and the movement in space? And all of that is only enabled by moving that stuff down to the edge. Again, not as many people are going to use an application that has to take a picture of their living room, then upload it to their laptop, and then sit in front of the computer and place furniture and wait for the sort of cloud services to churn. Another great example from the camera space that I don't know if anybody here has a fancy Mercedes, but they have had pedestrian detection in their cars for a number of years. Also, if you've used something like adaptive cruise control, that's another example of using camera sensor data and sometimes LiDAR data as well, and using a machine learning model that is sitting inside the car to determine, am I looking at a pedestrian? Am I looking at the back of another car? If you've ever driven the adaptive cruise control thing, you know, if a person weaves in front of you, it picks up that new target and starts spacing you off of that car. That's all edge intelligence. Those are all things that are powered today that people can use based on moving a machine learning model down to work on some sort of smaller processor. The Amazon Go store, this is the one in Seattle. I went there. It worked flawlessly. I mean, you can walk up to any shelf, pick up products, put them down or whatever. It takes an array of hundreds of cameras and lots of processing, but you can look at, you know, the entire process of the store, from sort of recognition, facial recognition, target tracking throughout. All of that is powered by machine learning, and it's a very cool application. And then this last one from the camera, this is a friend of mine's company. It's called Focal Systems. And they have built this system that goes onto shopping carts and into stores. And they use cameras that are, you can't tell, but they're facing out toward the sides. When you're pushing your cart down the aisle, they're using computer vision to look at all the shelves. That helps them do a couple of things. One, it helps them control inventory because they understand, is a shelf empty? Is there a certain hole in a wall of shelves? It also helps them with mapping, so they then understand, is the product where it's supposed to be? And that services information back up to like a, you know, sort of like a manager level person who's want to make sure that all the stores are consistent. But that's another great example of them using essentially an Android tablet, which is a commodity piece of hardware that didn't cost hundreds of thousands of dollars, to build something that would take a team of humans an entire night to go walk around and look at all the shelves and figure out what's in stock and not in stock. It's pretty amazing. Oh, that wasn't the last one for vision. This is another friend's company. So this is called Dahlia. Anyone here do smart home stuff? Anyone have lights automated, Philips Hue bulbs, things like that? Yeah, okay. So what they're trying to do is add a layer of context to it. Everybody that has smart home control right now realizes it's Not that smart. It's just exactly what you tell it to do. You say, turn on the light in the kitchen, it turns on the light in the kitchen. It doesn't sense what you're going to do. It doesn't have an idea that you're about to start cooking a meal. It instead just decides that it's going to keep that light on until you tell it to turn it off. DALL-E is trying to get past that. They are using commodity level cameras to infer context of what's going on in the house. Are you sitting on the couch and are you reading a book? That's a different light setting than if you're sitting on the couch and watching a TV show. That's a different setting than if you get off the couch and go to the kitchen. And what they're trying to move toward is a space where you no longer have to program these silly routines of, I'm going to do movie time, turn the lights off. It just infers it. There's no reason the camera can't take a look at what's happening in the room. And again, by pushing this stuff down to the edge intelligence, we don't need to tell some cloud provider whether you're naked on the couch. It's not something that we want to be sending up to the cloud. We want that computer processing to happen 100% in your home, detached from the internet, in airplane mode. The next sensor we'll talk a little bit about. This is a microphone. This is a big one in terms of the board, but the microphone powers a lot of stuff we are already used to controlling with our voices. So most people have used some sort of Alexa device or a Google Home. Most people, I don't know if they quite understand all of the components that go into it, but there's a large amount of processing that happens directly on the device for all of the wake words. It is it has the ability to react to multiple wake words, and that is a locally triggered thing. So although it does record samples of audio and push them up to Amazon for further contextual analysis of like what instruction were you trying to give, the actual process of triggering this is running 100% sort of edge intelligent. Very cool application of it and widely distributed and coming down significantly in cost. This is the Google Pixel 2, I think, is when they first released this. They took the microphone, using it in an ambient way, and they keep a local database of 75,000 song names and titles on the actual phones. And they use the microphone in an ambient mode to detect what song is playing around you. So this is like you're sitting in a cafe, it's just take a look at your phone and it automatically says, you're listening to this song. And Google would love to do that because they can maybe send music or YouTube and you can start paying them. But the idea is none of that processing is requiring the internet. They're not pushing something off, say, take this sample of audio, tell me what the song is, push it back down. It's happening passively. And ambient, although still really early days, is going to be a pretty big category of things that you have the processing cycles to do, so your phone or your car or whatever can be doing it, even if you're not specifically acting on that information. But it's kind of cool anyway, right? The other thing that comes a lot from voice, we're just seeing this kind of pop up now, but this is noise reduction. So right now the way that they do this with phones is by having a couple of microphones, and you take information received from one and you cancel out information received from the other. So it takes the microphone closest to your mouth and it cancels out the microphone in the back of the phone, which is sort of what it considers to be ambient noise. The next generation of that is actually training machine learning models to understand what noise is and what voice is, and then letting a little brain sort of sit on your phone and decide it. This again is like an example of what an expert could do with very little, of their time. If you had someone who was given an audio clip and they're like, was that a word being spoken into the phone, or was that some sort of background announcement, the airport sound, that kind of stuff? A normal person can figure this out, but we're able to now train little models on it and push them down. Last sensor we're going to go through. So this is an accelerometer, and most people's phones have them. Everybody's does. I don't know that a lot of people really consider them to be all that interesting in the sensor, but I think they're fascinating. These little guys, they can sample all the degrees of movement at something like 10,000 frames per second. It's probably the highest resolution in terms of data collected of any sensor you have in your phone, but it's not particularly sexy because it's not something like vision or audio. But they're really cool. Almost every augmented reality or mixed reality experience is powered by the accelerometer. It will use camera to show you what you're currently looking at, but it uses the accelerometer to understand all of the degrees in which you're tracking that object. So it might find, a surface with the camera, but then it needs to orient itself on how you're moving. Trust me, it's not running the same machine learning model over and over and over again on the picture, because that's much slower. Instead, it's using a fusion of the camera plus the accelerometer to determine how you're moving the phone through space. And just something as subtle as taking a step to the left, it gives enough force onto the accelerometer that those models can pick up on This is a local company called True Motion. I don't know if anybody's heard of this. Some friends of mine are over there, and they use machine learning to do car insurance. They sell to companies like Progressive, and they allow them to use a person's phone as a dongle, essentially, for their car. How is this person driving? So they can use it for stuff like distracted driving, if you're actually picking up and playing with your phone. But more importantly, they can use the accelerometer to determine whether you're making erratic movements, whether you're accelerating really hard, whether you're stopping really hard. I believe right now they only discount people's insurance, so don't worry, nobody's getting their bill jacked up just yet. But we're heading in this direction, right? Once we start putting accelerometers and data connections in every car that's sold, the insurance companies are going to start requiring this information. And that's all powered by accelerometers plus machine learning. So all of that stuff was sensor plus a little bit of expertise equals an application. And those are all based on just the sensors we're using today. There's lots of sensors that we're not using today. There are things like, infrared and multi-beam camera. There's the fusion of multiple different sensors. So there's going to be a lot more AI applications that get developed over time as we put more sensors in more devices. There are some problems with this. So I'd be remiss if I didn't talk about some of the things that can go wrong. If we're talking about like voice, for example, there are voice security, voice fingerprinting, voice commands, things that you might not want to happen unless you were there and present. And this is becoming more of a problem now because of voice synthesis. We're actually getting to the point where we can take machine learning models, train them on a large recorded audio corpus for a person, and generate audio clips that sound like that person. Now, I don't have anything to play for you tonight, but if you want to go look this up online, you can go find like President Obama having been saying things that he didn't say, basically using a generational technique with machine learning to do something that you wouldn't be able to tell the difference between him officially saying it and this algorithm saying it. You can do the same thing for Donald Trump if you want. But that's going to be a security concern, is whether people are going to be able to tell the difference between what really was said and what people are generating and they want you to think they said. This is another thing in the same realm called deep fakes. And I don't know why they do it with Nicolas Cage, but the idea is that you can take any picture and change a face or a aspect of that picture. And this one is a little clunky, but there are deepfakes out there that would trick you. And that means we're going to have to start thinking carefully about things like, well, if a camera sensor can be tricked this way, how do we know we can do something with detecting that it's the same person or the same face, or that we're trying to identify the same object? There's opportunities for those things to trick machine learning algorithms. And this is one of the most interesting examples. There's a technique called adversarial networks. This is a 3D printed turtle, I believe. And it's coming up, as far as the computer vision model is concerned, as a rifle. The way they do that is they've actually figured out a pattern to print on the back of that shell that the machine learning model does not have data that fits. And so it fits the best thing it can to it, which in this case happens to be rifle. I've seen the same experiment conducted with lots of different types of labels. It requires reverse engineering of the model, but imagine you're going into a store where it's Amazon Go style and it's pick up whatever you want. They use, facial detection or something like that. You could get around that by wearing some sort of a mask or wearing a hoodie with something printed on the back of it, and it loses track of the target. So although we have a lot of very powerful tools in our hands with machine learning, there are equally powerful ways to break all of them, whether it's voice or video or accelerometer data. And we're going to have to spend a lot of time making sure that our models, where they need to be safe and where they need to be secure, are being appropriately tested. A lot of folks are probably thinking about shipping an application with, it works. And like anything in software, yeah, it works for the 13 things you thought it would be used for, and it goes horribly wrong for the 2 things you didn't think. And these are examples of not just things that can go wrong because you didn't think of them, things that can go wrong because somebody else wants to defeat your system. It's not just, penetration testing. It's how is there a hole in the machine learning model that you created, and how do you know it's there? Great company if someone wants to start one, figuring out this adversarial stuff. All right, so jumping back out, or kind of down the stack a little bit, let's talk about the state of hardware, talk about chips, talk about devices. On the left there, is a Raspberry Pi, and that on the right is a computer vision task, looking at like a game that you play with your hand. But that's pretty cool. You can run a computer vision task on something that only costs $30. I think you could probably run this on a Raspberry Pi Zero, which is $5. But this is not the state of the art in terms of edge intelligence. We are now entering in the age of the NPU, as I like to call it. And NPU stands for neural processing. Just, sorry, quick show of hands. Does anybody know what neural processing units are? Okay, a little bit, couple hands. So a neural processing unit is sort of like a GPU, except it specializes in the tensor math that's required to compute machine learning inference. So when you're taking, like an image, for example, an image is an array of numbers that says, or two-dimensional array of numbers that says the pixel here represents these values, and then you do a bunch of math, usually multiplying numbers and manipulating the structure in order to get the output. Anyway, a neural processing unit has been optimized to do those things very, very, very fast. On the left is Samsung's current offering, which is called the Exynos. And on the right is Apple's most recent chip called the A12. We're going to show some benchmarks on this in a minute. But the A12 is the second generation of this for Apple. The Exynos is the first one for Samsung. And these guys, they don't enter these markets lightly. You've got to believe that if someone like Samsung and Apple and Qualcomm are shipping every new chip that goes into a handset with a NPU, that they're going to be using it for something. This isn't like, oh, we just added an extra hard disk and can store a little bit more data. This is a complete re-architecture of their chips. And it's not by mistake. They understand that there are a wave of AI and machine learning powered applications that are coming down to be run on these chips, and they're starting to build the hardware out. Apple's actually been building this for a couple of years because they have internally done this, even though it's not been exposed. So Touch ID, which is 4 years ago, something like that, that's powered by a machine learning algorithm that learns what your thumbprint looks like. Face ID with generation that learns what your face looks like. All of those things are enabled by them having a specific piece of their silicon that's really, really good at these types of deep learning problems. This is research that we've done at Fritz. And what this does is take machine learning models and run them on lots and lots of different mobile devices. Our SDK is on hundreds of thousands of devices out in the world, so we get a lot of information back on what these devices are doing and how they process. Important note here, this is a logarithmic scale on the left. So look at something like the iPhone XS. That, compared to one of the better Android devices, is still something like a 70x difference, okay? That's how far ahead Apple is in this age of the NPU. They have created a neural processor that is dozens of times better than anything any Android handset has today. And just want to see more of this data. I realize there's a lot on here. These are all Android devices, including some of the high-end ones, like the Google Pixel. There are some lower-end Android devices on here, and then these are all the iPads and all the iPhones. And this is running a mobile net model, which is a computer vision. But there's an incredible amount of computing power in these little things. The other thing that's happening here in the hardware area is, shouldn't be a big surprise, this happens in all hardware, but things with these neural processing units are moving downstream and moving down in price. What's happening is a chipset like the Exynos 9 or the A12 are starting in a flagship phone, which is a $1,000 device, maybe even more. And they are going out for a year or so, and then they figure out a more efficient way to manufacture those. They get to scale, start reducing the cost. They start going to mid-level devices. These prices, by the way, these are the cost of like the chip, not the device. This is like how much the individual component costs that actually compute a process. So system on a chip in a flagship phone might represent 10% of the cost of that phone. Then it moves to something like a camera, and it again represents 10%, but that camera is only a $300 item. And then it eventually moves down to something like an Echo, which they basically give away around Thanksgiving time, so maybe next week everybody can get one out. But the idea is that these chips, which were originally developed with the cutting-edge technology, have just moved way, way, way downstream. And that's an extension, I believe, of Moore's Law. What we're seeing is a transition right now from just sort of CPU, GPU world into NPU world, where we will continue this march toward more operations for fixed dollar costs into the foreseeable future. The reason I believe that is if we look at just what Apple has been able to do between 2 generations of chips. Their A11, which was in the first iPhone 10, first one with Face ID, was basically 10 times slower than what they have here. Their new chip, they moved to a 7 nanometer process. They have 10 billion transistors in that system on a chip, and they do 5 teraohms in terms of neural network calculations. This stuff's not on this chart, but I think it's a very, very important transition. I don't believe that we're seeing a slight extension to GPUs. I believe we're going to see a continued explosion of the amount of computing power we have available based on moving things to run as neural networks rather than just as stepwise operations. All right, moving forward. That's the current state of things. What you guys do. I'm only half joking about calling this Abdinoor's law. But the idea is sound, I believe. Parkinson's law says if you give someone a project and you say you have a week to get this project done, they'll find a way to take a whole week to get the project done. What I think is happening on the mobile and AI side is that developers will write software to consume any resource they have available. And if we see that these chips all have neural processing units, I have no doubt that developers will find a way to put them to good use. It might not always be computer vision and microphone-based stuff, and we'll talk about that. But the idea is that there's no freaking way they're putting a core in these chips that's just going to sit there idly. And there's no way the developers aren't going to think about whether they can squeeze a little bit more performance out of the application they're building by using the resources available. People go out of their way to figure out ways to, cache things, cache layers of information, or to move things to GPUs. And if you give them a new tool set, and that tool set also happens to be moving them up higher in that sort of Moore's Law world, they're going to start taking advantage of it. So that's what we're looking forward at. And how does that actually happen? So Andrej is, he's the head of AI at Tesla, unless there was another change over there, but he was the head of AI at Tesla at the time he wrote this. And it's the concept of taking software development as it is today and rethinking it through the lens of what we can enable with machine learning. Today, we are writing explicit instructions. We are thinking in terms of control flow, and we're figuring it all out in advance, right? There's a lot of developers in the room. You've all done this, and you've all been bit in the ass by the thing you forgot to tell the computer to do. Those are what bugs are, and then you fix them, and then you spend a while just looking at your keyboard going, I don't understand why this isn't fixed yet. I thought I fixed it. That is the unfortunate world we currently live in, where computers are relatively unintelligent. But we're moving to the world where they are more intelligent, and that means we transition to a new way of writing software, which is that you give a goal rather than steps. You say, get this thing done. I want to make sure that my application is always going to optimize for someone moving through the checkout flow. I realize there could be a billing disintegration. I realize there could be some sort of JavaScript error that gets thrown. I realize there could be some sort of, you mistyped your zip code or something like that. Instead of having a developer think about every single one of those possible edge cases and coding around it, we can train a small model to say, here's the goal we want to get. See if you can figure out how to make sure that that goal happens. And here's all the parameters you can change. You can help that person by bringing their attention back to a focus. You can switch the screen that they're on. You can bring another person into the mix if you need to actually figure out what a piece of information means. But we're telling software in the future how to act with a goal as opposed to how to act with every single instruction it needs to process. This is profound, I believe. And again, this is Andrej's thinking, not mine. But I want to share it with everyone because it's going to matter. We don't believe that software developers today are going to be all that different in 10 years. Most people think they're going to be writing the same kinds of programs. I don't know that that's true. I think machine learning is going to cannibalize our own jobs. Like, I'm a software developer and I don't, want to do less of this. But if all of the programs that I write could be better by me incorporating machine learning techniques to make sure that that's handling all of the errors and bugs, then I'm going to do it. And I think you guys should all consider the same. Another big boundary that we haven't crossed yet, but is pretty interesting, is data storage and retrieval. Traditional techniques, database indexes, we just use more storage. We take something and we say, let's write into a file that piece of information. Then let's take a piece of that information and use it to write into another file in a different order so we can go find it. That's all indexes are. They're just a bunch of crap on disk. or in memory. And all we're doing is writing fairly unsophisticated files somewhere that say, here's where my data is and here's how I find it. That's going away. We are seeing actual machine learning approaches be taking the same exact data and placing it and retrieving it with much, much better performance and much, much lower storage. This is Google, so these are some folks at Google that published this paper, and you guys can look it up, it's a public paper. But the idea is, you've got a little brain, and it's good at understanding the pieces of information that go in and out of a database. You say, here's a record, a user record, and you say, store it, okay? And then when you come back to it, you go, where did you store that thing? And because its little pathways were trained in storage information, storage of information and retrieval of information, it can just tell you immediately or very quickly where it put that information, as opposed to having to go read some file, look it up in the index, and then retrieve the information. I don't exactly even understand the full boundaries of this, but they were just testing it with a pretty simple use case of B-tree versus a learned index, and they're seeing fantastic results. This is not something that's been commercialized yet. This is not a product you can go out and buy today. It's still research, but it's coming, and I think it's going to be, again, profound for what we can do. Okay, so that was all the stuff on the future, and now I'm going to talk a little bit about my own company. Bad detail if I didn't call it product. But Fritz, we started because we saw these forces at play. We realized that there was a huge amount that could be done with AI. We realized that the majority of that stuff was going to happen out at the edge where the sensors and the cameras and all that kind of stuff are. And we also realized that the current state of the art for getting that to happen looked like hitting yourself in the head with a hammer. It was a very unfortunate set of tools and a very slow process. And we said, let's see if we can fix it. So this is what we've come up with. We focus entirely on mobile for today. We're working our way toward more edge devices over the next year or so. But we're focused on iOS and Android because there are billions of devices already out there. And as I showed you earlier with that hardware presentation piece, all of the chips that are really, really good at this stuff start at the high-end mobile phones and work their way downstream from there. So the odds are you're really good at running models on the flagship phone. Next year, you'll be running on the flagship camera, whatever it happens. We take machine learning and try to distill it down to an SDK that a normal developer can use, where they can install a dependency and start using machine learning rather than installing a tool chain, collecting data for 2 years and figuring out a model architecture, which tends to be the current state of the art. These are some of the examples of things that we have just packaged for immediate use by any mobile developer. And by the way, we have a free tier that goes up to a reasonable number of devices. So people can jump in and start using this stuff without having to worry about running up a tab. But on the left here is image labeling. In the middle there is image segmentation. On the right there is style transfer. And this actually is a slightly older version of style transfer. We have some even more impressive changes coming to that soon. But all of these things just look like style model.predict or image label.predict. You don't have to build the model. You don't have to train the model. You don't have to worry about deploying the model. We handle all of that stuff. And it works whether you're using one of the models that we've created or whether you're working on a customized model that you've created or whether you're doing something in the middle. You can take a style transfer model from us and retrain it with your favorite artist instead and then deploy that in your mobile application. And these are all camera-based things, but we're doing a lot of work in the near future on stuff that's not just camera-based, so looking at other sensors as well. Here's some actual applications that are using Fritz today. Plant Village here is an application for Android devices, and their target market is farmers in Africa. Farmers who happen to have Android devices, but don't happen to have a whole lot of expert information about growing plants. And it's important because when they lose crops, they actually starve. I shouldn't laugh because it sucks, but that is the problem that this team of researchers had set out to solve. They said, there's plenty of farming land, there's plenty of seeds, that kind of stuff. Where's the breakdown? It turns out the breakdown is that people don't understand what to do when there's a problem. So they've taken a model, which is a computer vision model there, and trained it on different crop diseases. And then inside the same application, they tell you what to do. So you point the camera at something, it finds the diseased parts of the leaf if there's a problem, and says, you have fall armyworm, here's how you deal with that. You need to add phosphorus. Go get some, add to the dirt. This happens 100% on device in airplane mode. So any farmer can be anywhere in the field with any plant, and it'll actually work. This would not have worked in any other way. They could not have relied on an internet connection to stream video. They could not have relied on people taking a bunch of pictures on their relatively low-end Android phones and sending them all up. They could not have depended on people to have the foresight to go out and spend one whole day farming and then one whole day learning and then go back and forth. They just put it all in your pocket. And we think this is super, super interesting. We love that team. There's a saber. So couldn't be any more opposite from something that's trying to save people from hunger. This is just a fun thing for people to play with. It's a mixed reality or augmented reality experience where you take a rolled up 8.5 by 11 sheet of paper, and it's using very sophisticated hand tracking and motion tracking algorithms. This is Hart. He's the guy who built this application. And he started this off as sort of a fun consumer project, but there are much more interesting downstream effects of what's coming here. He's created something that's really good at seeing what your hand or object is doing in 3D space. And that can be used to interact with things. So imagine that Wayfair application where instead of you kind of dragging and zooming with the phone screen, you just reach out in front of you and you can pick up the chair or you can move the table or you can scale things. It's sort of like Minority Report, but on your phone. And then MD Acne uses a on-device model to look at skin health. So they actually track whether people have blemishes, and they look at the same thing over time. So imagine going to your dermatologist every week. It would be incredibly expensive. They would probably get sick of seeing you, and they wouldn't even really remember what your face looked like the week before. This is technology that will do all of those things with the same level of accuracy and never forget. It can be trained 100% on what you look like, and it can tell whether you're getting better or worse. And this company happens to make money by selling a proactive type product. So they ship you a skincare regimen that goes along with the application. And as your skin improves in health, they can change the dosage on the medication that they send you. Very, very cool stuff. And all of this is being run on top of the Fritz software stack today. So benefits for using us. For mobile developers, we give them, again, that sort of SDK approach to using machine learning. Instead of having to go out and fire up Keras and do all this sort of stuff, for the use cases that we've prepared, they just use it like an API. Turn it on, start writing your application code around it, and the machine learning part will work fine. For people that are already building machine learning models and doing custom work, but they want to run it on an Android device or an iOS device, they use us for conversion, optimization, compression, deployment, analytics, all that kind of stuff. So once you get it to the point that you can ship it, we help you ship it. And we have an application in the App Store. Some of those screenshots you saw earlier came from it. This is just a demo app. It's not a product. We don't sell it or anything like that. Heartbeat is just a place where we put all of our current SDK features, so anyone who wants to play around with them can play around with them. That's also a completely open source project. So if you're looking at doing some iOS development or Android development and you want a place to start, you can just fork Heartbeat by Fritz and you can be doing your own machine learning work inside your app. And sorry, a little more background on that. We tend to use the frameworks that are already being supported by these devices. So on Apple, that means Core ML, Core ML2, and on Android, that means TensorFlow Lite and TensorFlow Mobile. Okay, let's wrap this all up. So what have we gone through today? What would be important to take away from it? Number one is that AI-first applications are no longer some sort of moonshot. It's not an idea that someone has in a laboratory. There are things in your phone right now, assuming you have any applications to talk about today. But there's stuff you can do immediately, and there's user experiences you can start thinking about powered by machine learning that weren't possible a year ago even. Number two, simple framework to determine if you've got something that might be an AI-first application is to ask yourself, is this a combination of what an expert would do in 1 minute with the information from a sensor? So is it that Shazam type thing? Is it the dermatologist check-in once a week? Is it some sort of motion detector that someone could feel? All of those types of things are very approachable ways to solve problems with AI today by thinking about sensor plus a small amount of information required. And then finally, edge intelligence, putting the sensors, models, data, all in the same place and making sure that we can run it really tightly and really fast is going to be greater than everything else. All of the cloud-based things that are running really large clusters of TPUs, I think in terms of number of operations, it will be dwarfed by the number of microcontrollers and phones and cameras that we have out in the real world running the exact same type of machine learning operations. And they will be largely invisible because nobody's really going to be grabbing that data in and out. That's one of the reasons we built Fritz, is because we thought if you're going to be pushing these types of things to run on these edge intelligent devices, you're going to want to know, how is it working? All right.